All right, let's talk about something we all use constantly, probably dozens of times a day, without ever really thinking about it. That little magic button that saves us from typos and bad edits, the undo button. But hiding behind that simple click is an absolutely beautiful piece of engineering. I mean, seriously, have you ever stopped to wonder how your computer does that? How it perfectly remembers every single thing you did in the exact reverse order, ready to just rewind time? Well, it's not actually magic. It's just a really, really brilliant idea. So let's do it. Let's pull back that curtain on this little piece of everyday magic. It all boils down to one simple question. How do you give a computer a perfect sequential memory? See, the trick isn't just that it remembers things. It's the way it remembers, in perfect reverse order. The very last thing you did has to be the first thing that gets undone. And that specific requirement right there, that's the big clue. And that clue leads us straight to the hero of this whole story. It's one of the most fundamental ideas in all of computer science. It's called a stack. A stack works on one super simple principle, perfectly captured by the acronym LIFO, last in, first out. It's exactly what it sounds like. Whatever you just did, that last action gets put right on top of a pile, making it the very first thing that gets taken off when you hit that undo button. You know, the classic analogy is a stack of plates at a buffet. When you add a clean plate, you put it on top. In geek speak, that's called a push. Then, when you need a plate, where do you grab it from? The top, of course. That's a pop. You're not going to try and yank one out from the middle of the stack, right? The whole thing would crash down. You can only access the top one. That is LIFO in action. And this is a perfect example of how that works. To reverse the sentence, the computer just pushes every single word onto the stack, one by one. It was the best, all the way to times. Then, to get the new sentence, it just pops them all back off. And what's the first word to come off? Times, because it was the last one in. It's so simple, and it's perfect. Okay, so that sounds easy, right? Problem solved. But like with most beautifully simple ideas, when you actually try to build it in the real world, you hit a snag. A really big, really common snag. So the first thing you might think of is, okay, I'll use an array. An array is just, well, it's a list with a fixed number of slots. You just decide up front, all right, my undo history is going to remember the last 10 things I did. Seems totally reasonable, doesn't it? So you start doing stuff, you type something, boom, that goes into slot number 1. You resize an image, that's slot number 2. And with every single action, you're filling up another slot in that list, one by one, all while you have no idea that you're getting closer and closer to the edge of a cliff. And then you try to do that 11th thing. But wait, you only planned for 10. Your list is full. And bam, the program crashes. You've just experienced what's famously called a stack overflow. We hit that hard limit of our fixed size array, and the whole system just gives up. And that is not the seamless experience we expect from our tools. So what's the fix? Well, what we really need is a stack that can just grow and shrink whenever we need it to, without us even thinking about it. And the solution? Oh, it's a real masterpiece of practical design. Okay, so the first naive thought is pretty simple. When you run out of space, just create a new list that's one slot bigger and copy everything over. Makes sense, right? The problem, it is horribly, horribly inefficient. As your history grows, it gets slower and slower and slower. It's a total performance nightmare. But here's the elegant solution, the big idea. Instead of adding just one slot, what if you doubled the size of the array every time it got full? So you go from 10 slots to 20, then to 40, then 80. Now that copy operation is still a big job when it happens, but, and this is the key, it happens way, way less often. This simple change is a game changer for efficiency. Okay, great. So growing is solved. But what about the other way around? What about shrinking? I mean, a good system shouldn't just waste a ton of memory. When we hit undo a bunch of times and the list gets empty, we should probably free up that space, shouldn't we? So the logical idea seems to be, well, if we double it when it's full, let's just cut it in half when it's half full. Sounds perfectly symmetrical. But this is a trap. It's a really subtle but nasty problem. Imagine you add one item, it grows. You undo it, it shrinks. You redo it, it grows again. You can get stuck in this terrible loop of grow, shrink, grow, shrink. It's called thrashing, and it would just kill your performance. And this brings us to the final beautiful piece of the puzzle. The solution is so simple. Don't shrink the array when it gets half full. Instead, you wait until it's only 1/4 full. That's it. That tiny change creates a crucial safety buffer. It guarantees that after any big resize, you have to do a whole bunch of cheap operations before you trigger another expensive one. And just like that, thrashing is gone. Now, this whole clever resizing strategy, it isn't just some neat little programmer's trick. It's actually a really powerful way of thinking about efficiency, and it's something that quietly powers so much of the technology we use every single day. This approach has a fancy name, amortized analysis. All it really means is that we stop obsessing over the worst-case cost of one single action. Instead, we look at the average cost over a whole long sequence. Yeah, every now and then there's an expensive resize, but that cost gets spread out over all the thousands of super cheap everyday operations. The cheap ones basically pay for the expensive ones. And this table lays it all out perfectly. Look, in the worst case, sure, a single push or pop could be expensive, but when you look at the amortized cost, the average cost over time, it's basically nothing. It's what we call a constant cost. And that's the magic number we're aiming for, 1. Because of this brilliant design, the average cost to push something onto the stack or pop it off is basically 1, a single, lightning-fast operation. And that, right there, is the whole point. The reason the undo button feels so instantaneous, so magical, is because of this invisible, intelligent design working behind the scenes. It's a philosophy that says an occasional expensive operation is totally fine, as long as it makes the everyday experience absolutely seamless. It really makes you think, doesn't it? The next time you're clicking around, what other simple, brilliant ideas like this are hiding just under the surface, quietly making our whole digital world work? What other bits of invisible genius are we taking for granted every single day?